As I said, the first algorithm we're going to discuss is the belief propagation algorithm, which works on tree-structured Markov random fields. So by that, I mean we have a Markov random field defined over variables, A, B, and it's structured in a tree form. That is, there are no cycles in this Markov random field. So one thing to note about that is recall that in a Markov random field, we can define potentials over any set of variables that are connected in a clique in the Markov random field. So we can, in a tree-structured Markov random field, we can define potentials over single variables and over pairs of variables. But notice that it's impossible ever to get a size 3 clique, because that would always form a loop, or a cycle rather, in the graph, and therefore the Markov random field would not be a tree. So if you know that your Markov random field is tree structured, then that's one thing that makes this nice computationally. You'll only ever see pairwise potentials. And also, more generally, there'll never be a cycle in the graph. And this is helpful for inference because kind of intuitively, if as a variable you have two neighbors, you know that they can't influence each other. They can't have any dependency except through the variable you're looking at. So we're going to see how that helps us in just a second. So any structure like this, where we have a loop in the graph, a cycle, that's not allowed. So I'm saying no, we're not allowed to do that. So we're choosing this because it enables the algorithm we're talking about next, which is called belief propagation, to work. In general, the algorithm doesn't work unless we are looking at specifically a tree-structured Markov random field. Note that we can also apply this algorithm to Bayesian networks, but a Bayesian network that has the structure of a tree is not necessarily the same as a Markov random field in the structure of a tree. Here's what I mean by that. Here is a Bayesian network, and it's in the structure of a tree in the sense that if you just look at the edges, there's no loops in the edges, either directed or undirected. But this does not correspond to a tree-structured Markov random field, because let's see what happens when we turn it into a Markov random field. Recall that when we do, we have to moralize the edges of each node's parents. So we get a Markov random field that looks like this. We had to add these two edges here to moralize the graph. Forgot that one. And we have these loops here. And again, we have potentials defined over these two triplets from the distributions over D and F respectively. That said, we certainly can have Bayesian networks that do correspond to tree-structured Markov random fields. A classic example of it is a hidden Markov model that I've drawn here. So if we have this network here, notice that every variable has just a single parent. So when you turn it into a Markov random field, we get this network, which is in fact a tree. So here's the idea of the belief propagation algorithm before we define it precisely. So we're given a big tree-structured Markov random field. By the way, if what we have is a Bayesian network, the first thing we're going to do is we're going to convert it to a Markov random field, and then we're going to do our inference from there. And we have one query variable, which we're going to call Q, and we have a bunch more variables, some of which are observed, that is, there are evidence variables, and some of which are hidden, there are we don't care variables. So notice that this is really, we can think of this as a big collection of potentials. So here we have a potential over Q and variable 2. I'm using numbers just for the sake of notation here. We have another potential over 1 and Q, another over 9 and 11, and so on. Now, the second thing we're going to do is we're going to get rid of all of our evidence variables from our potentials. So let's use this one as an example. In our original Markov random field, we have a potential over 3 and 1 over this edge here. Notice that 3 is observed. So this isn't really, so for the purposes of this question, let's say we've defined it that 3 equals 20 or whatever value. Let's just use 0. Then this isn't really a table over both 3 and 1 because only one value of 3 ever matters. So we can write this down as just a potential over variable 1 because that's the only one that varies. So we're going to get just those potentials there. So same thing goes here. For this potential, 9 is going to go away. We get just a potential over 11. Same thing goes here. We had a potential over Q and 9. 9 is observed, so 9 leaves our potential there. By the way, so we're going to do that for all of our variables. So we're not going to see our evidence variables in our potentials that we're going to use in the actual running of the algorithm. Also, because of our evidence, it's possible that we cut parts of the tree off. So notice here that this whole chunk of the tree has no impact whatsoever on our results, because as we talked about with deseparation, the value of variable 10, for example, is deseparated from Q because it has an observed variable between, and therefore they're conditionally independent. So we don't have to worry about this part at all. Okay, so what we get is a big collection of variables. The next thing we're going to do, just conceptually, is we're going to imagine hanging the tree from our query variable Q. So we're going to pick up Q and essentially let the tree dangle from that variable. So we'll get something that looks like this, where notice that we've gotten rid of all our evidence variables, like 8 and 6. We've gotten rid of this whole subtree because that doesn't matter, and we end up with this tree here. So the reason we did the dangling is we're going to do an algorithm that that traverses this tree, starting from the leaves going up. So this way of kind of orienting over Q gives us an order for our algorithm that we're going to use in a second. So now in this reduced tree, we have new potentials defined on just these variables we have here. So note that in some cases, like in the case where previously we would have had a potential over 3 and 1, we end up with just a potential over 1 here. But we have a big set of potentials, unary potentials over each of our variables potentially coming from situations like this, and pairwise potentials over pairs of our variables for every edge in this reduced tree. And just a reminder that here's what we're trying to compute. We want the probability of Q, all the possible values of Q, given E. I'm using E for all our evidence, which in this case is specific assignments 2, 3, 6, 8, 9, and 12, which equals 1 over Z. And by the way, this Z isn't necessarily the same Z for our original Markov random field, because here this is the Z corresponding to some specific set of evidence. So if we were to write out this Z, it would be sum over Q as well. But we're not going to worry about that. We're just going to lump it all into this big normalization constant. And that equals sum over all the variables except for Q of all of these potentials we have left. So this is our optimization problem. And notice that this is still tough because we have this big sum over all of our variables that we don't care about. Okay, let's actually define the algorithm now. So we're going to use this as an example where we have a tree here that has a root that we were calling Q for the query on the last slide. The core of this algorithm is we're going to compute a belief factor for each variable. In this case, we're going to focus on xt, which equals the probability of xt given vt minus, which we are using to mean everything below xt in the graph as it's oriented here, which we can define as follows. So we can calculate that belief as 1 over zt, that is a normalization constant that's specific to variable t, times psi t of xt. This is any univariate potential we have in the original MRF that we're given, times the following, which is a product over our children, that is the children of child t. Now note that, of course, in the MRF, there's no direction to edges. So by child here, we mean nodes below us in the way we've oriented the graph relative to the query. So here, our children, the children of t are s and u. The product over those children of this thing, message from c to t of xt. So I haven't defined this yet, so this isn't going to make any sense. So we've defined this belief, or we're going to define this belief based on information from our children, and we want this to equal the probability of x given all the information about its children. By the way, note the minus signs in the superscript here. That's because this is the first pass of this algorithm. I'm going to talk about a second pass in just a minute. Okay, so this doesn't make any sense until we define these messages. So let's define that. We define the message from s to t, which again, notice that s is a child of t, as the following. Now, this message is going to be a factor over xt. By the way, notice that about the belief as well. The belief is a factor over xt. That makes perfect sense because it's a probability distribution over xt. Therefore, of course, it's a probability table over the possible values of xt. Message from s to t is going to be a factor over the values of xt, which is going to be equal to the following. The sum over the possible values of xs, which again, xs is the child, xs, of the following. The pairwise factor over these two variables, again, that's from our original markup random field. Let me mark that one as well as the original factors we're using, times the belief of x, which again is a factor over xs. And then so this thing here, if we were to write that out, that would be a factor over xs xt, but then we're going to sum out xs because we don't need that for the message in order to get a factor over just xt. And that's going to be used to calculate the belief over xt. And then notice that in order to calculate the belief of xt, we need the message to t, which uses the belief of xs. So in order to actually calculate this, we would have to recursively continue this computation. We would use this expression here to calculate the belief over xs, which requires that we have the message going to s. So the way we do this algorithm is we start from the leaves. Note that leaves have no children, so this is going to be a product over nothing. So in the leaves, we get just this factor here for our belief. This is going to be a factor over just the values of xt, which in this case would be s1 and s2, u1, u2 respectively. Those are our leaves. Then we need to calculate a normalization constant. Notice that this is easy, specifically in this case, because to calculate this normalization constant, we just have to sum over the possible values of xt. So calculating this is going to take time just proportional to the size of xt. So that's our kind of base case of our recursion, or the first step in our algorithm. Then, now that we've calculated the beliefs for each of our leaves, I'll circle them to indicate that we've calculated the belief for those using this expression here. Then we're going to calculate the messages. Using this expression here. Note that to calculate this expression, let's just double check that we can calculate it. That involves the belief over our leaf. Good, we've got that. And our factor, well, that comes from our initial markup random field, so we have that as well. So good, we can calculate that. Now we calculate belief of any variable that's one step away from a leaf using this expression. Let's just double check that we can do that. We need our univariate factor, if we have one, which, good. We know what that is. That's from our initial value. We have to take the product over our children and multiply in those messages for the particular value of xt. That's good. We just calculated those, so we're good. So we can calculate that. So now we've computed the beliefs over s and u in this case, and then we continue. We calculate these messages, belief over t, and then finally the message from t to the root and the belief over the root. And the belief over the root is our answer. So in fact, once we calculate the belief over the root, we can report that as probability of query given our evidence. That's the thing we wanted, so we're done. Let's look at the running time of this algorithm. So there's kind of two steps that we need to look at. There's the calculation of the belief. That calculation takes time equal to, well, what do we have to do? Well, we're going to produce a factor over the possible values of xt. So for each possible value of xt, we have to do some calculations, and to figure out what that value is, we have to look up a value in this factor, and we have to multiply together our the values of our different children. So let's assume that each of our variables has dimension d, or domain size d. That is, each variable can take on d values. So for a binary random variable, d would be 2. And let's assume we have n variables. So this belief update step, by the way, notice that the belief update for a specific variable could take as much as dn time, because we have to do this calculation for each of the possible values of xt, and for each one we have to multiply in some arbitrary number of children, which could be as much as n, if this were like a star-shaped graph. But notice that we use each message only once. So overall, this belief step, even across all the variables, is going to take time proportional to d times n. Now let's look at this message passing step. What do we have to do? We have to compute something for all the possible values of xt, and then we're going to have to compute this for also all the possible values of xs. So what we're going to get is d squared, because again we have to go over all of xt and xs, and we're going to have to do that once for each of our n variables in order to, we're calculating for all of our message passing steps. So each one takes just d squared time. We have to do it n times. So our total running time of this is O of d squared times n. And it's, so these two steps are combined. So, and this is the more expensive step here. So we don't have to worry about this. This is our overall running time for this belief propagation algorithm. Overall, d squared times n time. And that's pretty good. So notice that this is linear in our number of variables. So even for a really huge graph, or a really huge probabilistic graphical network, like let's imagine we're in the case of our medical network, where there might be thousands of different tests that we performed. Or in the case of a Markov model, we might be doing some computation over thousands of time steps. Now, probably in the medical case, it's probably unlikely that we would get a tree-structured Markov random field. So maybe we shouldn't worry about that one. But specifically in the case of a Markov model that has a chain structure, which is a chain, by the way, is one example of a tree, or really any other graph, even if it's really big, as long as it's in this tree structure, we can do our inference in time, linear in n, quadratic in the size of each, the size of the domain of each random variable, but that's usually not too big of a deal. Usually our variables are, either binary or some small domain size. So the thing you have to worry about is how it grows as a function of the number of variables n. But one thing you might have to worry about is, well, we just computed the the probability for a specific query, Q. So in order to, if I wanted the distribution over each of our unobserved variables, that's a very common thing to want to do. For example, in the case of a Markov model, if I have some unobserved state at each position, let's say this is a Markov model for finance, and our unobserved variable at each position might be whether or not the economy is in a recession in a given year. Sometimes I might just want to ask the model, do you think I'm in a recession at this year? But more often I might want to ask something like, okay, give me, for every year, give me the probability that that year is a recession. To do that, using just the algorithm I just showed you, I would have to take this d squared n algorithm and run it n times. So I would end up, to do the whole thing, I would end up with d squared times n squared. That's quadratic in n, that starts to get expensive. Fortunately, it's quite easy to modify this algorithm to give you not just the probability over the root, but actually the probability over all of our variables. It involves passing messages down the tree, very similar to the ones we passed up the tree. And then we're going to update our beliefs. So you'll see this in a textbook. Again, I'm not going to do this here, but these are the minus beliefs, indicating they're the beliefs we get just from going up the tree. In the textbook, there's beliefs defined without the superscript, and that involves a product over not just the messages coming up the tree, but also the messages coming down the tree. I'll leave that to you to read in the textbook. Okay, so that's our belief propagation algorithm. Again, this is very efficient, runs in time linear in the number of variables, gives you an exact solution, but the downside is this applies only to tree-structured Markov random fields.